welcome to this problem walkthrough. In this session, we will explore LeetCode problem number 1548, the most similar path in a graph. We'll dive into the problem statement, discuss the key concepts, and work through the solution step by step. Let's get started. In this problem, we are working with a graph that consists of nodes and edges. The graph is represented using three main components: an integer n which tells us the number of nodes, an array roads that specifies the connections between nodes, and an array names where each node is associated with a unique city name. The roads array defines the graph structure, with each pair, u, v, indicating a bidirectional road between nodes u and v. Along with this graph, we are given a target path, which is a sequence of city names we want to follow as closely as possible. Our goal is to find a path through the graph such that the city names along the path have the smallest possible edit distance from the target path. The edit distance is simply the count of positions where the names differ between two paths. Finally, we need to return the most similar path as a list of node indices, and if there are multiple paths with the same edit distance, we can return any one of them. Now, let's take a closer look at the input and output format for this problem. The first input, n, specifies the number of nodes in the graph, with a constraint that n is at least 1 and at most 100. The roads array contains pairs of integers, where each pair represents a road connecting two nodes. The total number of roads can range from 0 to the maximum possible number of unique edges in a graph with n nodes. Next, the names array contains exactly n unique city names, one for each node, and the target path is a list of city names that represents the sequence we aim to match. For the output, we need to return a list of integers representing the indices of nodes in the most similar path. This path minimizes the edit distance compared to the target path. Let's look at the first example to understand this more concretely. Here, the graph has 5 nodes labeled with the city names ATL, PK, LAX, DXB, and HND. The roads define the connections between these nodes, and the target path is specified as ATL, DXB, HND, LAX. The task is to find the path through the graph that best matches this target sequence. In this example, the path 0, 2, 4, 2 is returned. If we map these node indices to their city names, the path corresponds to ATL, LAX, HND, LAX. This path is the most similar to the target path, with an edit distance of 0, meaning there are no mismatches between the target path and the graph path at any position. In the next example, we have a graph with 4 nodes connected in a cycle. The nodes are labeled with the city names A, B, C, and D. The target path is A, C, D, B, and the solution returns the path 0, 1, 2, 3. This path perfectly matches the target path when mapped to the city names, with no differences in any position. This demonstrates that the solution is able to identify an exact match when it exists, even in graphs with cyclic structures. Finally, in the third example, the graph contains 3 nodes with city names X, Y, and Z, and the target path is Z, Y, X. The solution returns the path 2, 1, 0, which corresponds to the exact sequence of city names in the target path. This shows that the solution correctly handles smaller graphs and can find a perfect match even when the graph is fully connected. To summarize, the problem includes constraints like the graph being undirected and free of duplicate edges, and the solution must consider edge cases such as disconnected graphs, multiple valid solutions, or graphs with cycles. The target path will always contain valid city names, but it might not always match perfectly with the graph, so the solution must find the closest possible path in terms of edit distance. To solve problem number 1548, which involves finding the most similar path in a graph, we need to minimize the edit distance between the path and a given target list of city names. A straightforward approach would be brute force, where we generate all possible paths of length k, calculate the edit distance for each path, and pick the one with the smallest value. However, this approach has a complexity of O, n to the power of k, asterisk k, where n is the number of nodes and k is the path length. This quickly becomes computationally infeasible as k or n grows, due to the exponential number of paths. Instead, we can use a dynamic programming approach to optimize the solution. Here, we define dp, I, j, as the minimum edit distance to reach node j at step I. The recurrence relation calculates this value by considering all neighbors from the previous step and adding a cost based on whether the current node's name matches the target name. This avoids recomputation by building on previously calculated results. Additionally, a backtracking array allows us to reconstruct the actual path after filling in the DP table. The dynamic programming solution offers significant improvements in efficiency and scalability. The time complexity is O, k*n*e, where e is the number of edges in the graph. This is because, for each step, we process all nodes and their neighbors. The space complexity is O, k*n*, which accounts for the DP table storing the minimum edit distances at each step for each node. Another potential approach is a Dijkstra-like algorithm, where the edit cost serves as the distance, and the goal is to find the path with the minimum cumulative cost. However, this method introduces added complexity due to the need for a priority queue and careful path reconstruction. Ultimately, the dynamic programming approach was chosen because it strikes a balance between efficiency, clarity, and ease of implementation. By leveraging the graph's sequential structure, redundant calculations are minimized, and the backtracking array ensures we can efficiently reconstruct the optimal path after computing the DP table. When comparing the three approaches, brute force is clearly impractical due to its exponential time complexity, making it unsuitable for larger inputs. The dynamic programming approach, on the other hand, provides an optimal balance of efficiency and maintainability, with a manageable polynomial complexity. While a Dijkstra-like algorithm is theoretically feasible, it introduces additional overhead with priority queues and path tracking, which makes it less intuitive to implement for this specific problem. Overall, the dynamic programming approach stands out as the most practical and robust solution. It not only meets the problem's constraints but also ensures clarity and simplicity in both implementation and debugging, making it the ideal choice for addressing the challenge effectively. To solve LeetCode problem number 1548, our goal is to find a path of fixed length k in a graph that minimizes the edit distance compared to the given target path. The edit distance measures mismatches between city names in our path and the target path. For example, if the city at position I in our path does not match target path, I, it contributes 1 unit to the cost. The problem can be framed as a graph traversal task with constraints. The path must stop after k steps, and we need to minimize the cost efficiently. Dynamic programming is a natural choice here, as it lets us explore all possible paths systematically while avoiding redundant calculations. This approach takes advantage of overlapping subproblems, enabling us to compute the optimal solution step by step. To formalize our dynamic programming approach, we define a state dp, I, j, which represents the minimum edit distance to construct a path of length I ending at city j. To compute this value, we look at all neighbors u of j from the previous step, I1, and select the one that yields the minimum cost. The recurrence relation is straightforward, dp, I, j, equals min, dp, I1, u, plus mismatch underscore cost, j, target path, I, where mismatch underscore cost, j, target path, I, is 1 if the city j does not match target path, I, and 0 otherwise. Initialization is simple. For the base case where I equals 0, dp, 0, j, is just the mismatch cost of starting the path at city j. As we iterate through the path lengths from 1 to k1 and evaluate each city, we update dp, I, j, using the computed values from the previous step. To reconstruct the optimal path later, we maintain a parent table that records the previous city for each state. Once we have filled the dp table, we can reconstruct the optimal path using the parent table. First, we identify the city j at step k1 with the minimum cost, which is stored in dp, k1, j. This marks the endpoint of our optimal path. Using the parent table, we backtrack step by step, from k1 to 0, to retrieve the entire path. This ensures that the path we construct is not only valid but also minimizes the total edit distance. Now, considering the algorithm's efficiency, the time complexity is derived from iterating over all possible path lengths, cities, and their neighbors, leading to O, k*n*m, where m is the average number of neighbors per city. The space complexity is O, k*n*, because we store the dp table in parent table. By efficiently leveraging dynamic programming, we ensure that each subproblem is solved optimally and reused, while the parent table simplifies path reconstruction. The final output of our algorithm is the reconstructed path of length k with the minimum edit distance. To implement this, we initialize the dp and parent tables. The base case fills in the initial costs for starting the path at each city. Then, for each path length I from 1 to k1, we iterate over all cities and calculate the minimum cost for transitioning from their neighbors. If the cost improves the current state, we update both the DP and parent tables accordingly. Finally, we identify the endpoint of the optimal path by finding the city with the minimum cost at DP, K1. This algorithm is structured to ensure that every step builds upon the previous computations, guaranteeing an efficient and accurate solution even for large graphs. To complete the implementation, we use the parent table to backtrack and reconstruct the path. Starting from the city with the minimum cost at DP, K1, we trace back through each step using the parent pointers, appending cities to the path as we go. Once the backtracking is complete, we reverse the path to obtain it in the correct order, from start to finish. This reconstructed path is then returned as the final result. The combination of dynamic programming for optimal cost calculation and the parent table for path reconstruction ensures that our algorithm is both efficient and easy to implement. The result is a path of length k that minimizes mismatches with the target path, solving the problem effectively within the given constraints. We begin by importing the necessary modules, such as defaultdict and deque, to help us manage the graph and perform various operations efficiently. The first function we define is Floyd_Warshall, which implements the Floyd-Warshall algorithm to compute the shortest paths between all pairs of nodes in the graph. We start by initializing an adjacency matrix dist where the diagonal values, representing the distance from a node to itself, are set to 0, and all other distances are set to infinity. This matrix will be updated as we process the input edges. For each edge connecting nodes u and v, the distance is set to 1 in both directions since the graph is undirected. Next, we apply the core of the Floyd-Warshall algorithm, iterating through all possible intermediate nodes k to check if there exists a shorter path between any two nodes I and j through k. If so, we update the distance in the matrix. Once this process is complete, the matrix contains the shortest path distances for all node pairs, which we return. After that, we define the most similar method in the solution class. This method starts by building an adjacency list from the road connections, making it easier to traverse the graph structure. Each node is linked to its neighbors in both directions, forming the representation we'll use for further calculations. We then proceed to handle the dynamic programming portion of the solution. The variable k is initialized as the length of the target path, and we create two 2D arrays, dp to store the minimum edit distances and parent to track the previous node leading to the current state. Both are initialized with appropriate default values, infinity for dp and -1 for parent. For the first city in the target path, we populate dp 0 by comparing each city's name with the first entry in the target path. If there's a mismatch, we record it as a cost of 1, otherwise, the cost is 0. Next, we iterate through the target path and fill the dp table for each subsequent city. For each city, we examine its neighbors in the graph and compute the cost of transitioning from the neighbor to the current city. This cost depends on the previous dp value and whether the current city's name matches the corresponding target path name. If the total cost is lower than the current recorded value in dp, we update it and record the parent node. After building the dp table, we determine the city with the minimum cost at the end of the target path and backtrack using the parent array to reconstruct the path. Starting from the last city, we append each city to the path and follow the parent pointers in reverse order until we reach the start. Finally, we return the path in the correct order by reversing it. Here, we begin by importing the necessary libraries and defining the main method for our solution. The function takes in the number of cities, the roads connecting them, the names of the cities, and the target path. First, we build an adjacency list to represent the graph. This allows us to store the connections between cities in a way that makes it easy to traverse. For each city, we initialize an empty list, and then for each road, we add the neighboring cities to the respective lists in our graph. Next, we define the length of the target path, k, and set up two 2D arrays, dp and parent. The dp array will store the minimum edit distance for reaching each city at every step in the path, while the parent array will help us reconstruct the path later. To ensure correctness, we initialize all values in dp to integer.max_value and all values in parent to -1. Finally, we set up the base case in the dp table for the first city in the target path, where the cost is 0 if the city name matches the first target name, and 1 if it doesn't. Now, we proceed to fill the DP table for the subsequent cities in the target path. For each step in the path, we iterate through all cities and their neighbors in the graph. We calculate the cost of transitioning from a neighboring city to the current city, adding 0 if the city name matches the current target name, or 1 if it doesn't. If this cost is lower than the current value in DP, city, we update it and record the neighbor in the parent array. This ensures that at each step, we keep track of the optimal path leading to the current city. Once the DP table is fully populated, we determine the city with the minimum cost at the last step of the target path. We iterate through all cities to find the one with the lowest value in DP, K1, storing this city as the endpoint of the most similar path. With the minimum cost and endpoint identified, we are ready to reconstruct the path. To reconstruct the path, we use the parent pointers stored during the dynamic programming process. Starting from the endpoint city identified in the previous step, we trace back through the parent array to build the path in reverse order. For each step in the target path, we add the current city to the front of a linked list, then update the current city to its parent. This process continues until we reach the first step of the path. Once the path is fully reconstructed, we return it as a list of integers representing the most similar path in the graph. This completes the implementation, providing an efficient solution to find the path with the minimum edit distance to the given target path. To solve the problem, we start with a simple example. The graph has 4 nodes, and the roads define the connections between them. Using these, we construct an adjacency list to represent the graph. This list tells us which nodes are connected to each other. Next, we initialize a dynamic programming table and a parent table. The DP table will store the minimum edit distances for matching the target path at each step, while the parent table will help us reconstruct the final path. Since the target path starts with a, we initialize the first row of the DP table accordingly. If a city's name matches a, the cost is 0, otherwise, it's 1. This setup prepares us to calculate the optimal path in subsequent steps. Now, we populate the DP table. For each step in the target path, we calculate the minimum cost to reach each city by considering its neighbors. For instance, when matching C, we look at all cities that can transition from the previous step and update the costs based on whether their names match C or not. This process is repeated for the next step, D, ensuring we track the lowest cost and record the parent city for backtracking. After filling the table, we identify the minimum cost in the last row, which corresponds to the end of the target path. Using the parent table, we then trace back to reconstruct the most similar path, which in this case is 0, 2, 3. In the second example, the graph is larger and has multiple possible paths. We again start by building the adjacency list to represent the graph structure. With the DP and parent tables reset, we initialize the first row based on the first target path value, a. As we progress, the DP table is filled step by step. For B, we calculate the costs to reach each city based on its neighbors, updating the table and parent pointers accordingly. The same process is repeated for D and E, ensuring that at each step, we consider all possible transitions and their associated costs. This careful updating guarantees that we can track the optimal path through the graph. Finally, we determine the minimum cost in the last row of the DP table, which corresponds to the last step of the target path. From this point, we use the parent table to backtrack and reconstruct the path. For this example, the result is 0, 1, 3, 4. In the third and final example, the graph forms a circular structure. The adjacency list reflects this by showing that each node is connected to 2 others, creating a loop. The DP table is updated similarly, with careful handling of the circular nature to ensure correct parent pointers. This allows us to reconstruct the path 0, 1, 2, 0 as the most similar path for the given target path. To analyze the time complexity of this solution, we begin with the graph construction step. Here, we build an adjacency list from the given road's input. Each road is processed exactly once, and since the number of edges, denoted as roads, is proportional to the number of nodes n, this step runs in O(n) time. Next, we have the initialization of the dynamic programming table, or DP table, which has dimensions kxn. This represents k, the length of the target path, and n, the number of cities. filling all k*n cells requires k*n time. These are the preliminary operations that set up the foundation for solving the problem efficiently. The next step involves the dynamic programming transition, where most of the computational work occurs. Here, we use nested loops. The outer loop runs k1 times, as we process each step of the target path after the first. For each step, we loop over all n cities, and for each city, we process its neighbors. In the worst-case scenario, if the graph is fully connected, each city can have up to n neighbors. Combining these iterations, the total complexity for this step becomes k*n*n, or k*n squared in the worst case. Finally, the path reconstruction phase involves backtracking through the parent table to retrieve the most similar path, which takes k time. When we combine all these steps, the dynamic programming transition dominates the overall time complexity, making it k*n squared. Now turning to space complexity, the first component is the graph representation. Using an adjacency list, the memory usage is proportional to the number of edges, roads. In the worst case of a complete graph, this becomes n squared. The dynamic programming table is the next major contributor. With dimensions kxn, the DP table requires k*n space. Similarly, the parent table, which is used to reconstruct the path, also consumes k*n memory. Lastly, we have auxiliary variables such as min_cost, end_city, and the reconstructed path, which together require k space. When we sum these components, the total space complexity becomes n squared plus k times n. However, since n squared dominates in the worst case, the overall space complexity simplifies to n squared. When comparing this dynamic programming approach to a naive solution, the efficiency becomes clear. A brute force method would involve generating all possible paths of length k and calculating their costs. Since there are n(k) possible paths, and evaluating each requires k time, the total time complexity would be n to the power of k*k, which is infeasible for larger values of n and k. In contrast, the dynamic programming approach leverages overlapping subproblems and iteratively computes the minimum cost, reducing the complexity to k*n squared. This is a dramatic improvement. Analyzing the best, average, and worst-case scenarios, we see that in sparse graphs, where nodes have fewer neighbors, the effective complexity is closer to k*n*m, where m is the average degree of a node. For typical graphs, the complexity remains around k*n squared, and in the worst case, with a complete graph, it is also k*n squared. Finally, let's justify the asymptotic complexity mathematically. The dominant factor in the time complexity arises from the nested loops. The outer loop iterates over k steps, the inner loop iterates over n cities, and for each city, its neighbors are processed. Since each operation within these loops, such as updating the DP table and comparing values, is performed in constant time, the overall time complexity scales as k*n squared in the worst case. As for space complexity, the adjacency list for the graph and the DP and parent tables dominate the memory usage. This leads to an overall space complexity of n squared in the worst case, as the adjacency list grows quadratically within 4 dense graphs. This concludes the time and space complexity analysis for the dynamic programming solution. When working on this problem, there are a few common mistakes to watch out for. First, using an adjacency matrix instead of an adjacency list can be problematic, particularly for sparse graphs. Adjacency matrices require n squared space, which becomes inefficient as the graph grows large, especially when many nodes have few edges. Adjacency lists, on the other hand, only use n plus m space, making them much better suited for sparse graphs. Another mistake is attempting a naive depth-first search without memoization. This approach tries to explore all possible paths of length k, but without caching intermediate results, the time complexity balloons to n to the power of k, which is infeasible for larger constraints and will likely result in time limit exceeded errors. Lastly, misunderstanding how to calculate the edit distance incrementally can lead to incorrect results or overly complex logic. Instead of comparing the entire path to the target list only at the end, it's crucial to update the distance step by step as the path is constructed. Now, it's essential to address some additional pitfalls. Ignoring edge cases can significantly impact the correctness of your solution. For example, you must account for situations where the graph is disconnected or where the specified path length k exceeds the maximum possible path length in the graph. Overlooking these cases could lead to runtime errors or incorrect outputs. Another common issue is poor initialization of the dynamic programming table. If you forget to set up the base cases where the path starts, the entire recursive relationship can break down. Since dynamic programming relies heavily on propagating accurate intermediate results, getting the initialization right is critical to solving the problem correctly. To excel in interviews with this problem, focus on the key insights. At its core, this problem combines graph traversal techniques like BFS or DFS with dynamic programming. Being able to identify overlapping subproblems and optimize them using memoization is a crucial skill. Recognizing patterns can also be helpful. The problem shares similarities with shortest path algorithms but introduces the unique challenge of minimizing edit distance. Drawing comparisons to algorithms like Dijkstra's or Floyd-Warshall can provide a helpful framework for your solution. When communicating your approach, it's important to articulate why you chose a specific graph representation and why memoization is necessary. Be sure to highlight your understanding of trade-offs, such as balancing time and space complexity. Finally, prepare to discuss why brute force approaches fail and how dynamic programming reduces the complexity from exponential to O and *k*d, where d represents the average degree of nodes. This problem also connects to other LeetCode challenges, which can provide additional context and practice. For example, LeetCode number 472, concatenated words, involves using dynamic programming to handle overlapping subproblems. LeetCode number 787, cheapest flights within k-stops, focuses on minimizing a cost metric while adhering to constraints, which is conceptually similar to minimizing edit distance in this problem. LeetCode number 983, minimum cost for tickets, also involves optimizing costs under constraints, and LeetCode number 1143, longest common subsequence, is a classic dynamic programming problem that deals with sequence alignment, closely tied to the logic of edit distance. Exploring these problems can deepen your understanding of the techniques and patterns that apply here. Finally, let's consider some alternative approaches to solving this problem. A brute force depth-first search explores all possible paths of length k and calculates the edit distance for each. While this method is simple to implement, its exponential time complexity of O, n to the power of k, makes it impractical for anything but the smallest inputs. A more efficient approach is to use dynamic programming with memoization. By maintaining a table, like dp, node, step, to store the minimum edit distance for reaching a given node at a specific step, this method achieves a much better time complexity of O and *k*d. However, it does require careful initialization and a solid understanding of the recursive relationships. Another option is a greedy approximation, where you make locally optimal choices at each step to minimize the edit distance. While this is fast and easy to implement, it doesn't guarantee the global optimum, especially in graphs with complex structures. Each approach has its trade-offs, so it's important to choose the one that best suits the problem constraints. Great work! In this session, we tackled LeetCode problem number 1548 and learned how to solve it using dynamic programming. We discussed the time and space complexity, key takeaways, and when to use this approach in similar problems. Thanks for joining, and don't forget to like, share, and subscribe for more coding tutorials. Keep up the practice and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!